Yeah, so in this talk I will start with a short introduction about star-like oscillations and present a sample of red giants, and then focus on the method that I'm working on and present some first results obtained with this method. So as you have seen already, star-like oscillations are basically acoustic waves propagating in convective outer envelope of low mass stars. They can be identified with three quantum numbers, so radial order and angular degree and azimuthal number. As you see in these colored plots, they produce different distributions on the surface of the star. There are tiny brightness variations of the order of the ppms, and at the present time they are observed in more than 15,000 stars from main sequence to red giants. They are characterized in the Fourier domain by this typical Gaussian envelope of the oscillations, where you can see characteristic parameters like the nu max, the frequency of maximum power, and the amplitude of this oscillation envelope that are related to fundamental cellular properties like surface gravity, temperature, and luminosity. If you look closer, you see the repeated structure of these modes, and the characteristic spacing of this structure is what we call the last frequency separation, delta nu, and it's a function of the mean density of the star. So as the star evolves, the amplitude of the oscillations increase, and the frequency of maximum power, nu max, and delta nu decrease. If we look even closer to a single mode of oscillation, we see that since they are damped oscillations, it can be reproduced by a Lorentzian profile. That means the mode is basically resolved, so the observing time of the time series that we are using is longer, much longer than the lifetime of the mode. Characteristic parameters that define this profile are the frequency of the centroid, of course, and the line width that is related to the lifetime, and the height in the power spectrum. So three free parameters, we say, to define one single oscillation mode, as Thomas said before. Concerning the red giants in particular, as the star evolves from the main sequence to the RGB phase, we see that the P mode frequencies decrease and the G mode frequencies increase. And they start to couple, producing an effect that you observe especially in the dipole modes of the star. So in this case, the single P mode dipole mode is replaced by a forest of peaks that are deriving from the coupling with the G modes. So the analysis of the spacings of these mixed modes is basically allowing you to distinguish between helium core and hydrogen shell burning red giants. If we look at this plot, we see a synthetic population of composite red giant stars made by Andrea Emilio for the CoRoT field. We can identify in this diagram different types, different classes of red giants. We see as first the high luminosity red giant branch stars on top. Then we find the helium burning red giants, those characterizing the first red clump, and then the secondary clump stars that you have heard already yesterday in Moser talk. In particular, in this talk, I want to focus to a type, a class of these red giants that are the low luminosity and low mass red giants. And there are quite a few in the entire sample, about 5%. And they can be delimited by a nu max, say, of the not lower than 110 microns, more or less. And they are important to constrain stellar evolution rates and test also stellar evolution and structure and pulsation codes. So for the sample that I've taken into account, we started from an original set of stars investigated by Daniel Huber that we present in this diagram, where we plot the new max against the temperature. And you can see the evolution of the stars going this way. So from main sequence to the red giant branch. And we have, for this sample of 1,600 stars, global parameters like nu max, delta nu, and amplitude. We applied a restriction based on the available studies for the mixed modes, and a restriction on the nu max according to the range I've told you before. So taking only the highest signal to noise ratio stars, we ended up with a sample of 21 low mass, low luminosity red giant branch stars that you see in this diagram as before, where we also have plotted the amplitude in a color scale. So they nearly cover all the range in temperature and nu max. An example of two power spectra of these stars is given in this slide, where you can see that for these two stars, despite of the fact that they have a very similar nu max, you have a quite different structure of the mixed modes. So in the top panel, in this case, there are much fewer modes than in the lower one. We used new data sets of Kepler, spanning about 1,500 days of observation. So we have a frequency resolution of 8 nanohertz. So concerning the aim of this work, so in order to introduce the method, we have to present the Big Bang analysis. Thomas did that already before, but just to briefly remind you, Big Bang analysis means that we want to extract all the information available for each of the modes present in the stars. And to do that, we need a first estimation of the background, so any signal in the star that is not related to the oscillations, and then fitting the Lorentzian profiles to each of the modes, and do a mode identification for each of them. So the aim of the work is in practice to perform an efficient Big Bagging of all these red giant branch stars, and then a detailed study of all the astroseismic properties that we derived. The challenge is that in these stars, we have several modes between 40 and 90, and the dimensions of the models that we have to use for the fit can easily grow over 100 free parameters. And so this results in a very slow computation. So the question is how to make the multi-parameter fit efficient. This is relevant especially if we want to fit several stars. And the second question is how to consider a frequency peak significant, which is one of the most problematic things also. Because many times it's ambiguous and we don't know in general how to do that. The solution that I provide is based on the Bayesian Nested Sampling, again, as Thomas explained it before, because it's a very suited algorithm for high-dimensional problems. Existing codes implementing the nested sampling are multi-nest, which is in Fortran, and Diamonds, that is a recently developed code in C++, and you can also find more details in my poster, number 41, concerning this code. So just to give you an idea of the power of this method, so classical numerical sampling methods like Markov chain Monte Carlo, that I plot here this histogram with an arbitrary scale of 1 million sampling points required to provide a solution, say, to a given problem, have been reduced to about a factor of 2 of 100 with multi-nest. And with Diamonds, we reduced that number by another factor of 3. So this is already a quite nice result in terms of computational efficiency. So concerning the analysis of the power spectra, how to apply the method. So instead of fitting the entire power spectrum in this case, we divide it into chunks, having a length of nearly the large separation. And so we apply the method iteratively in order to cover the entire range in frequency, covering the Gaussian envelope of the oscillations. So in the end, we have between 10 and 43 parameters for each chunk that we fit. And diamonds can do that with 2 minutes computation in on laptop. It's a separate process, and you end up with a robust Bayesian estimates for the 3 parameters. And it's already a successful approach for main sequence stars. You can see also in the poster. So what model did we use? We used the Lorentzian profiles, as already explained, for all the resolved modes, but different mixed modes appearing in the power spectra have not been resolved yet, even with nearly 1,500 days of observations. So for this particular case, where you only see a spike, we use a different profile, which is a sinc squared, as you would expect from a non-resolved mode. So these also reduce the number of parameters to 2 instead of 3. So we only fit the centroid and the height, in this case, since the peak has the width of the frequency resolution. So mixed model, including both profiles. And concerning the peak significance instead, we again recall the concept of the Bayesian evidence, which is provided in Bayesian analysis. So Bayesian evidence is a dimensionless quantity that increases as the fit increases and decreases with the increasing of the 3 parameters of the model. So simple models are preferred in general, and it's a weight of the model that we want to fit. So this is difficult to compute with standard MCMC because it's a very expensive computation, but with diamonds and nested sampling codes in general is a direct output. So model comparison becomes really easy. To test this criterion, we did a test with simulations. 1,000 simulations, where 100 of them were including a peak, and the remainder were at just noise level. So we fitted 1,000 models, assuming there was a peak, and another 1,000 models assuming there was nothing. And in the end, defining this detection probability, which is merely the weight of the evidence with a model that takes into account the peak, and considering the 99% probability to detect the peak, we found all the peaks in the simulations. So this gives you an idea of the strength of the evidence. So application to 1 star in this sample that I show here. It's a nice spectrum containing several modes of oscillations, peaked around 160 microhertz. And first of all, we estimated the background, as I said before. So these results in the fit, the final fit represented by the red line, where we fit the different components introduced in the previous talk. And we adopted the formulation of Kallinger for this case with the 2 granulation components. After that, we performed the peak bagging as explained in the previous slides. So here you see a chunk of this power spectrum where you observe the region of the mixed modes, and then one quadruple and radial mode on the right side, and even an helical tree mode on the very left. This is the resulting fit in blue, where you see the 3 arrows, black arrows, marking the position of the unresolved mixed modes, while for the reminders we have used Lorentzian profiles. So they are partially resolved in this case. If we look closer, we see that 3 of these peaks are very low in height. For these peaks, we tested a peak significance, and we find out that 2 of them were accepted, and 1 was to be considered noise peak. So in the end, This is the final result of the entire peak bagging analysis on these stars. We had a total of 63 modes, of which 21 were unresolved mixed modes. And then we had 7 radial modes, 6 quadrupole, and 3 helical 3 modes. And we tested in total 35 peaks with the evidence criterion. This is just to show you a very quick result with the analysis of the line widths of the different angular degrees. As you can clearly see, we have a depression in the line width trend occurring close to the position of nu max. It's something expected and is consistent with the theoretical studies where you know that the depression is caused by a resonance with a superadiabatic layer in the star, and it's also observed in main sequence and subchar star. And lastly, also the acoustic glitches. So by plotting merely the simple large separation as a function of the frequency in the star, you can clearly see the sinusoidal behavior. And this is both for radial and quadrupole modes. And this is also observed in other red giant stars and is related to the presence of sharp structural variations inside the star. So very likely second helium ionization zones. And they can be used to determine actually the position of these structures inside the star. So to conclude, low luminosity and mass red giant branch stars are few, so only 5% of the sample. Their study is important for testing stellar formation rates and stellar structure and evolution codes. And with so long observations so now available by Kepler, the peak bagging analysis is really necessary if we want to go further and understand more, because global analysis cannot do much more at this point. And the peak bagging of these stars seems to be very well performed by the Diamonds code, and also the peak significance criterion proves to be very reliable. So this puts us towards an automated, or at least partially automated, peak bagging analysis for several red giants, and this is already feasible with this code for the main sequence stars, even challenging F-type stars, and there's something also shown in the poster. So, thank you.
I think Tim was first on that one.
Thank you. That's really nice, Enrico. I have a comment about L equals 2. You're
Yes.
fitting L equals 2 as a singlet, but it's a multiplet.
Yes.
And it has a spacing which is √3 smaller than L equals 1. So I suggest you can do that easily. And also your line widths for L equals 2, therefore, at the moment are meaningless because you're measuring a multiplet, which is really there.
Yeah, actually, we could do that, of course. In this case, I was not assuming there was any splitting for that mode, but it's something we can, of course.
I can see it on the plot.
Yeah, sure.
Yeah.
I've seen also different cases as well.
Yeah, I'm not sure I understand how you compute the evidence. You say you divide the spectrum in chunks, and then you do the sampling chunk by chunk.
Yes.
And then, well, if you want to compute the evidence for the models, you need all the parameters. And how do you compute this integral, knowing that you did the sampling chunk by chunk?
You can do that if you are only taking into account the peaks falling inside that chunk. If you also do the test, enlarging the range and doing the same comparison, you will see the result is not changing. So in practice, evidence is only depending, of course, on the model that you use, but also on the data that you are taking into account. So when I do the fit, I literally drop down all the data points that are not inside the chunk. So that's also changed the thing.
Okay, any other questions? If not, let's thank the speaker again.
Okay.